Sheng today for our Digital Future seminar. And Anzhi now is a postdoc in DCS and Department of Mathematics. And before he joined KTH, he graduated from Peking University as a PhD in 2025. And from 2022 to 2024, he was a visiting scholar in the University of Pennsylvania. And there he was working with Professor Joshua Hawking. And Andrew's research interest lies in the evolutionary game theory, network science, and their interplay. He was also contributing his research to understanding the emergence of collaboration and altruism on complex networks, including temporal and high-order networks. He is also interested in applying mathematical models to reproduce statistical properties observed in the empirical network datasets. So without further ado, let's welcome Dr. Anzhi Sheng.
Thank you, Steven, and thanks everyone for joining. My name is Anzhi Sheng, and I'm a postdoc in Division of Decision and Control Systems and Development Math. And today I will briefly have an introduction of this. I think it's a very new dynamics of complex networks. And the goal of today's talk is to first have an overview of how this research area evolves and the idea or the model in this field, and also what kind of open questions remains.
Louder.
Okay.
Otherwise, you need a microphone.
Okay, so I'll be louder. So yeah, so let me first have an overview of today's talk. I will first introduce the background and the motivation of average game theory, and then I will have a brief literature overview, and then I will introduce some applications of average game theory, and also I will introduce some open questions in this research field. So one of the key questions in average game theory is try to explain why we have why this cooperation can emerge in our human societies and also in nature. So cooperation is very common. We collaborate with our colleagues, and we in our human society we always work with others. So and cooperation is very important for the stability or the development of our organization. For example, if you can look at the first figure, there is a group of ants, and they're trying to climb from one leaf to another one, but there's a very big gap. So they try to finish this very difficult task. And for each single ant, they probably don't have this ability to finish this task. But when they collaborate with each other and form as a group, they build this bridge, and some ants can climb from this leaf to another one through this bridge. So this is actually so cooperation in this case can be seen as a key factor to the emergence of this kind of collective intelligence, because we know for each single ant they cannot finish this very difficult task, but when they form as a group, they can finish this very difficult task. And actually the energy of the whole group is not just the simple summation of the energy of each single ants. They actually have a nonlinear effect when they collaborate with each other. And this phenomenon is also widely exists in our human societies. So that's why we will care about cooperation, because it's, as I just said, is a key factor as the emergence of collective intelligence. And especially nowadays, we talk a lot about AIs and group intelligence, and there are a lot of research that show that cooperation is very important to form this kind of collective intelligence, like the example I showed in groups of ants or in human societies. And so for the researchers in African theory, we use the model in game theory to model this interactions between individuals, or like the interaction among a group of individuals. So the very basic model is from the game theory. So we talk a lot about cooperation and we could say altruism, but we still don't answer a very elementary question: is the cooperation that hard to emerge in the population? Because if the cooperation or the corporate behavior is very easy to evolve or to emerge under natural condition, we actually don't need to ask how to promote cooperation, because it's very easy to evolve. So the answer to this question is, it's not always that hard, but we always facing some situation in our real life when there is a conflict between individual interest and group interest. And when we face this kind of conflict, we're always trying to choose like defection, which is kind of behavior that to pursue the individual interest. But for the development of the whole organization, we actually need to choose cooperation for which is beneficial for the group interest. So in this case, we should come up with some mechanism to promote cooperation. But before we introduce the mechanism, I want to use this model to fully capture the conflict between individual interest and group interest. So this is called a very classical model in game theory called the prisoner's dilemma. And the background of this model is there is two prisoners, and they were like isolated held in prison, and they were integrated. And each prisoner have two choices. One is collaborate with another prisoner, which we call cooperation, which means they keep silent. And another choice is to convince, which is the defective behavior. So when these two prisoners both choose cooperation, then both of them will be sentenced to 5 years in prison, or for 1 year in prison. And when they both choose defection, then they were sentenced to like 5 years. And if one of them choose cooperation and another one choose defection, then the cooperator will be sentenced to 20 years. And the defector will be released immediately. So we could use this payoff matrix to conclude this element and values. So if we look at this payoff matrix, you could find that the numbers in the bottom line is higher than the numbers in the line. This means no matter what your opponent choice, you choose it. The best strategy is always defection, which means like if you want to maximize your own benefit or payoff, you have to choose cooperation or defection, because defection is actually the best response in any scenario. But if you compare the benefit between the collective defection and collective cooperation, you'll find that when these two individuals collaborate with each other, the sum of the year is actually only -2. But when these two individuals defect with each other, the payoff is like -10, which is lower than the -2. So this collective cooperation is actually better for both individuals, because it's also beneficial for their own their individual interest and also for the group interest. But under natural condition, if these two prisoners are very rational, they can only choose defection. So under any like natural condition, this cooperation can never forth. So that's why we call it a dilemma, because even though we know like collective cooperation is better for everyone, but since these two between each other, well, they are not best buddies, like they are not relatives, they will definitely choose deflection. So this is the dilemma. So for the person dilemma I introduced before, we have like four parameter. So it's a little bit complicated. And this donation game is like a specific form of prisoner's dilemma, which is you only have two parameters here, and is simpler than the general form. And we will often use this donation game when we talk about two-player games like in a population. So the background of this game is the cooperator will pay a cost C to provide a benefit B to the opponent, no matter what strategy this opponent chooses, and the deflector will pay nothing and also provide nothing. So when the benefit B is larger than C, larger than 0, this is a specific type of prisoner's dilemma, because you could find that D is the best response, but the collective cooperation has a higher benefit. So this game has some like realistic examples, like blood donation, where you donate blood, you pay cost C to others who need blood and give them a benefit B. Also, like you share some study notes online, you pay some time to like organize all the study notes and publish online. Yeah. So another kind of game. So so sometimes we're not only interested in two-player games, we're also interested in like multiplayer games. So this public game is like a multiplayer version of Prisoner Dilemma when we talk about multiplayer scenario. And so in this game, a cooperator will pay a cost C. Like donate a social goods in a public pool, and the deflector is nothing. And then this public pool will produce a total benefit proportional to the number of costs donated in this public pool. And actually, it's just the number of costs multiplied by a synergy factor R. And this total benefit will be uniformly divided to all participants, no matter what participant choice in the contribution phase. So if you look at the right panel, you will notice that the deflector will also get some benefit. So in this scenario, when the synergy factor R is smaller than the number of participants L, this is a prisoner's dilemma. And the example includes like the taxation for like public transportation or public facilities, or we have a group homework involves those students work together. So this is the case for a multiplayer game. So we have known that we want to promote cooperation in the population, but for game theory, we actually cannot solve this question, because when we talk about evolution, we need to have a new axis like time to in the model. But in game theory, actually the whole model is kind of static. So that's why we move to this evolution game theory to introduce the axis of time to try to solve this question. But actually, only moving from game theory to evolution game theory cannot solve this question. Because if you can look at these two very classical models, the first one is we call the replicator dynamics, is a deterministic model, and it happens in an infinite well-mixed population. So since the population is infinite, then we use the frequency of cooperator to check the changes of of the cooperation in population. And we have this like ODEs. So this ODE actually model the how the frequency of cooperator changes. And UC means the payoff of a cooperator, and U bar means the average payoff in the population. So this ODE means, like, for example, when the payoff of a cooperator is higher than the average payoff of the population, then the frequency of C will decrease or will increase, and this increase will stop when the payoff of C is equal to the average payoff of the whole population. So this is the deterministic model. And the second one, we call it the Morin process, and it has a finite well mixed population. This model is a stochastic model. And the background of this model is like, we first select an individual to produce an offspring, and the selection is the selection is proportional to the fitness of individual's payoff, and the fitness is actually a linear function with individuals payoff. So an individual with a higher payoff is more likely to select and to produce the offspring. And once this offspring, we have offspring, and this offspring will randomly select individual in the population to occupy that site. So we have this probability to increase a cooperator or decrease a cooperator. This process can make sure like the total number of the population is fixed over time. So, and in the first model, we care about the stability of the equilibrium when PC equals 1. And second, because we don't have any mutation, we care about the probability of reaching the cooperator state. And using some analysis, we could know population can never emerge. Well, so this two model works for any games. And when the game is a prison dilemma, for example, the donation game, cooperation can never evolve in these two games. So our questions still remain, like what kind of mechanism can promote cooperation? So in 2006, Martin Novak have a paper in Science, and he like proposed like 5 very basic rules for the evolution of cooperation. So the first one we call kin selection. So in this kin selection model, individual has a new like matrix like called the relatives. So if an individual is like to you, then if the relative have higher fitness, then you yourself will have an additional, or we call it indirect fitness, because your relative have a higher fitness. And in kin selection, we can know like cooperation can evolve. And the second one we call it like direct reciprocity. So in this model, individual will not only interact one shot, they will interact repeatedly, and they will choose an action based on the your opponent's historical actions and choose a more appropriate action to make sure the cooperation can maintain. The third one we call indirect reciprocity. This means when you interact or when you choose to cooperate with your opponent, there is an observer. They can observe your action and give you a very good reputation. Then once you have a good reputation, then in the next round, others will have a higher probability to collaborate with you. But once you become a defector, then no one will give you any like help, and you will have a very low payoff. Then you will, after evolution, everyone probably will choose to be a good behavior, have a good behavior and good reputation, and try to cooperate. And the fourth one is a group selection, where the individual are like separate into several groups, and the individual will compete with each other in groups. But also the competition also happen between groups. So we call it like a multi-level selection, because the selection happens within groups and also between groups. the final one is my main research interest, called the network reciprocity, where an individual have a specific interaction topology. They can only interact with the individuals as their neighbors, and also like copy the strategy when they are connected to each other. Yeah, so this will be the main thing I will introduce.
Are these like necessary conditions, these five, or they're all conditions that help the emergence of cooperation?
They are not necessary conditions. They are like, so there are a bunch of models. They can all conclude at these five mechanisms.
But without the five, you would not get a cooperative. No cooperation will emerge without any of these.
So I think that's a great question. So at least right now, I know like all the mechanisms can somehow be concluded as one of these five rules. Yeah. Or probably you have some combination between these rules. Yeah. So this is like the basic procedure for when we talk about network reciprocity. So first, we have a network represent the interaction structure of the population, and this network, each node in this network is represent an individual, and the link between nodes is like represent the interaction between two individuals. So at each time step, we have two phases. The first one is interactions. Individual will interact with their neighbors and have a cumulative payoff or an average payoff over all the interactions. And then they will use some specific strategy updating rules to update the whole population. Probably only one individual will change this strategy, or probably the whole population will change their strategy. So in this effort, so we have two types of model. The first one is we don't have any mutation in the model. So after sufficient evolution, the whole population will definitely reach the homogeneous state. One of the two homogeneous states. The one is everyone choose cooperation, and another one is everyone choose defection. And we will use the fixation. We will use the probability that the population reaches the all cooperation state as our measurement to quantify the evolutionary success of cooperation. And this probability is called the fixation probability of cooperation. So when there is mutation, which means like when you trying to update your strategy and you copy someone's strategy, you accidentally choose the opposite one with a probability mu. So in this case, you could escape from the homogeneous state. Then there is no solving state in this model, and we use like the average frequency of cooperators in the stationary distribution to quantify the average success of cooperation. Yeah, and then I will introduce some very important reference in network reciprocity. So in network reciprocity, we actually is an intersection of averaging game theory and network science. So I will introduce. So the reference above this axis is for the average game theory, and the reference below this axis is reference for network science. So for the first reference I would like to introduce is this paper published in 1992, I guess. So this is the first paper to introduce network population structure in averaging game theory. And the population structure they consider is square ladders with periodic boundaries. And the payoff matrix they consider is we call the weak prisoner's dilemma, because the payoff of DD is the same as the payoff of CD. But in the paper they also said when the payoff of DD is 0 become epsilon, all the result holds. So I guess this conclusion also seems to like strong Fresnel's dilemma. And the updating rule here is when individual choose to update their strategy, they will imitate the neighbor with the highest payoff. So if you look at the figures, the blue color means someone choose cooperation, and the red color means someone choose defection. So we know, like in well-mixed population, cooperation cannot be evolved, but in the square lattice, we could see that even B is larger than 1, we have cooperators in the populations, but it's quite straightforward. Is when we increase B, the frequency of cooperators will decrease. So if we look at the top panel, there is a very interesting phenomenon. Is all the cooperators are like gathered as a cluster, and all the defections are surrounded these cooperators. So the reason why cooperators can maintain in the population is because once we have this population structure, then all the cooperators can gather as a cluster, and the cooperator within this cluster have a higher payoff than the defectors surrounded by this cluster. So cooperator can maintain the cluster, and the defector cannot invade this cluster. But when the population is well mixed, everyone should interact with each other, then defector can immediately invade this kind of cluster, and the cooperation will collapse. So for that paper, they consider like square lattice and other kinds of networks, but all the network structure they consider is kind of stylized. This is because at that time we don't have too much network models, and so they can only consider some stylized network structures. But like at the end of So these two papers are very important in network science. So the first paper published in 1998, I guess. Yeah, 1998, they come up with a model called to generate smaller networks. And for the latter one, published in 1999, they have a like preferred attachment model to generate this scale-free networks. So for the first model, they kind of reproduce the small world property of observing scale-free model. They reproduce the whole law distribution in empirical networks. So after they have this network models, every game theory researchers use these two models to did a lot of simulations, and the operation can emerge in those kind of. But this, and we turn to this paper published in. This is like a very important theoretical model to show a very simple rule to determine whether cooperation can evolve in structured population. So in this paper, they use pair approximation and diffusion approximation to approximate the fixation probability of cooperation in structured population. So the population structure they consider is homogeneous or heterogeneous networks of average degree k, and they consider donation game, and they use this that burst updating rules. And in this updating rules, only one individual will update their strategy, and the probability of copying their neighbor's strategy is proportional to your neighbor's fitness. So this simple rule is like because we have a benefit B and C in the donation game, the rule is the ratio of benefit B and the C is larger than K. So when when the E over C ratio is larger than the average degree K, we say this cooperation can be favored by selection in the population. So this condition is derived under regular graphs. But if you look at the Monte Carlo simulations, you could find that this condition probably is not that accurate in heterogeneous networks, but it still like provide a kind of necessary condition for cooperation to evolve. And also this paper, there are a bunch of papers using multicast simulations to discuss the emergence of cooperation. So this paper published in 2000, the public goods game in homogeneous networks and also the scale-free networks. And they find out that they used this synchronized pairwise comparison where each individual have a chance to update the strategy at each time step. And they find that the average frequency of cooperation is higher when the social type follows a polar distribution, which means the heterogeneity of population structure can promote the average of cooperation. The intuitive of this condition is like when there is like hub node in the networks. So when the population is heterogeneous, there are several hub nodes in the population, and once this hub node become a cooperator, then this hub node can like organize a very large cluster, and in this case, de facto can very hard to invade this cluster, and that's why the hub node can lead the whole population goes to the more cooperative state. And also, yeah, that is for the simulation and public goods game. And in 2009, there is a paper. They have this a very interesting theoretical result. So this result is for any two-player games, and they find that the condition for cooperation to be favored is like have this we call structural coefficient theorem. And there is so when we have this general payoff matrix, and the condition is like sigma A plus B is larger than C plus sigma D, and this parameter sigma depends on the population structure, the update rules, or like the rotation rate, but it's not dependent on the. This means for a given network and a given updating rules, if we could calculate this sigma, then we actually can solve a bunch of different payoff matrices. Because once we have this sigma, no matter how change this payoff matrix, we can immediately know if cooperation can evolve under this payoff matrix. And actually, the same authors published a paper in 2011. They extended this result to like multiplayer games, and they have the very similar sigma, but this sigma becomes like 3 in multiplayer games. So yeah, they have this structural coefficient theorem, but they actually don't solve question like how to calculate this sigma, because when they have, you could look at this figure, when the population structure differs, this sigma is different. But the systematic approach to calculate this sigma is still lacking at that time. Oh, so this question will be it was solved in 2007 and 2022. But before that, I want to introduce something in network science. So we talk a lot about network reciprocity, but the whole network is static. They are not temporal. But so around 2010, thanks to the development of some modern technology, they accumulate a bunch enormous network datasets, includes the time steps. So they have a bunch of temporal network datasets, and in that time, research in network science trying to come up with some models to generate temporal networks. So a temporal network is actually formed by several network snapshots. For each snapshot, the network probably not connected, but once you aggregate all the snapshots together, it will form an aggregate network. It's connected, and so a static network can be seen like temporal network with a very low resolution. So that's why at that time we only consider static network in average gain theory because we don't have a very good model to generate temporal networks. But we will come back to that. So this is the paper in 2007. They used the Pearson theorem to provide an analytical result for fixation probability of cooperation on any population structure. This is a very important paper. Using this fixation probability, they also provide a more accurate result for the B over C ratio for cooperation to evolve. And this B over C ratio is related to the random walk on a given population structure, and also the coalescent time on this. So if you look at this figure, like the left here, you could see the dots are simulation result, and the vertical line shows the critical ratio derived by this theoretical method. Compared to the result in 2006, the simple law result, it is more accurate, even for it actually accurate for any. Like for BA model is just the scale-free networks is fully heterogeneous, but the result, the theoretical results can match with the simulation results. Since we can solve all carry all the critical ratio, here they done two things. The first thing is like he calculate all the critical ratio for all the graphs of size 5, and there are 21 graphs of size 5. And only 7 of them have a positive critical ratio. This means, so only the critical is positive, cooperation can evolve in the population. And when the critical ratio is negative or infinite, cooperation can never evolve. For example, if we know like cooperation can never evolve in well-mixed population. And so this is the well-mixed population. So from the perspective of critical ratio, then this critical ratio is negative, and that's why cooperation cannot evolve in the well-mixed population. So if we only look at the result for small graphs, we may wonder like there is only a minor part of networks have a positive result, and we cannot say like network can promote cooperation. But actually, in our real in the real world, the network is a little bit larger, and the structure is more random than this small graphs. So they actually like investigate 1.3 million larger random graphs, and the size is ranging from 100 to 150. So this figure shows the result, and they use different kinds of network generation model to generate this random graphs. And you could see like over like around 71% of this random networks have positive critical ratios, and this could show like networks can promote cooperation. And this reference is for the title. This paper like give us a systematic approach to calculate that sigma. So, and they use this approach to solve the result when the averaging gain theory when the averaging process have mutations. So for the previous paper, they use fixation probability, which means they assume there is no mutation during the evolution. But in this paper, we assume there is a constant mutation rate, and since they can in this paper can calculate the that sigma, then they can use the result to calculate the average frequency of cooperation in stationary distribution, and use that result to identify if this a given population structure can promote cooperation. Yeah. So yeah, all of this. So all the result I introduced is based on static networks, and so there, around like 2020, there is a bunch of researchers focus on this temporal networks. So for temporal networks, there are basically two types of results, two types of model. The first model is the network transition is based on it is periodic, or they transmit based on a Markov chain. And another kind of model is the network, it grows with time and will stop growth when the population is stabilized. And for this papers, they have the goal is to try to identify if like temporal interactions can, for example, decrease the critical ratio, or have in the same situations, can the frequency of cooperation increase by temporal interactions. So they have a very similar conclusion, like temporal interaction can promote cooperation or even rescue cooperation. This means like for a network, for example, a well-mixed population, the critical ratio is negative, but once you let this network like only for a given time step, only a small part of interaction are active, and all other interaction are inactive. Generate this kind of temporal interactions, then this critical ratio probably transfer from a negative one to a positive one. This means this temporal interaction can. Yeah, and so all these papers before, they consider this temporal network models, but they do not consider like the most important statistical property observed in temporal networks. This is because at that time they don't have a fair network model to generate. Like for example, in the first paper, use this model to generate the most important statistic property in temporal network we call the burstiness, and in the second paper, the authors use a generative model to generate temporal hypergraphs with significant properties observed in the high order temporal networks. So based on these two models, like the future research can be on temporal network can be take the burstiness and temporal hypergraph property into consideration. But before consider the temporal hyper one, this new research have considered the high order networks and the structural evolution of high order networks. So the difference between the structural evolution on like pairwise networks and high order networks is like on high order networks, they could simultaneously have different orders of interactions. And then, for example, if you look at the left panel, they simultaneously have second order interactions and like third order interactions. Then individual may simultaneously engage in like pairwise game and also 3-player games. And in this case, the game form could be nonlinear with respect to the number of operators as their neighbors. So, and in this paper, they also provide the analytical result for under which cooperation is favored by natural selection. And the result I show is considered when the networks only involves second order and third order interactions. And this FBFC is labeled by 2 and 3, and they are for sure that related to the random walks on the hypergraph, and also a higher dimension of collapsing time on the hypergraphs. This research have the main finding of this research is they find like when the population structure have very distinct community structures, then the introduction of higher order interaction can reduce the critical ratio, and which means this higher order interaction can promote cooperation. And we know like this community structure is very common in empirical networks. So that's why like in our like human societies, we are not only collaborate with others through pairwise one, we also like collaborate with others in groups. This is because we have this community structure. Except for all these theoretical studies, they also have some experimental studies. For example, like for the first one, they have an experiment to show like when this network reciprocity is not because, for example, we are connected to each other. It's not because we are relatives. We might be strangers, but we have some. We need to have some connections. Then we form a social network, and in this study they find like the existence of social networks can do promote the level of cooperation with the population. And the second one, they trying to explain why dynamic interaction or temporal interaction can promote cooperation. And the third one, they try to verify that simple BCK rules in all human societies. And they do like find that when B over C is larger than K, the cooperation can be stabilized. Yeah, and also I want to introduce some application of infinite game theory. So first is about this political science. So in this paper, they use average game theory model and network science to like analyze voter games in a structured population. And they come up with a concept called information gerrymandering. And this concept basically told us like when two parties are competing with each other, a party, even they have less supporters, they could finally win the voter when they have a strategy they use a specific strategy to alter the population structure, and they probably have to win even though they have less supporters, they can win more states or win more partitions and finally win the voter. So they use this model to explain like the US election in the history. Well, and the second application is they use the repeated games to explain how fake news or this misinformation spread in the population. So this is actually the competition between the interaction between a news producer and the consumer. And they find that even though a consumer is trying to find the truth of a news, they still have a probability to transfer a fake news or misinformation because they somehow induced by the news producer. Also, this application is like they use the repeated games and the model to consider the agent stochastic game, and they theoretically derive we call a dominant strategy, which can like control the payoff of another individuals. And they also use this strategy to compare with the result derived from the pulse gradient method, and they have somehow like a very consistent result. So this is the thing I list for as a conclusion. So we So the left column is what we have now, and the right one is what we don't. What we have now is like we have a theoretical approach or framework for each single 5 basic rules for cooperation. But somehow, for example, in our human societies, we probably have a model like the combination of these 2 rules. For example, we live in a structured population, but the interaction between each other is not one shot, but probably repeated. So for this model, they simultaneously have like network reciprocity and this direct reciprocity. And another example is like definitely have an observer when we connect with each other. This network reciprocity probably need to combine with indirect reciprocity. So we don't have a model to cast together or a unified framework. So the second thing is we have this 2-agent model, as I showed before, with very complicated like policy learning process, and also we have this multi-agent model. It's very simple, like imitation or just horizontal strategy. This kind of very simple, but and we definitely don't have a multi-agent model with complicated policy learning process, and even in a well-mixed population. And the more interesting thing is like we can solve this kind of question in structured population. And the third and fourth thing is a little bit of mathematics. Like the third thing is all the analytical result or the approximation are based on collection theory and under weak selection. But sometimes, for example, when we consider the competition between cells, the selection is actually not that weak. They're a little bit stronger. So our theoretical result is unable to capture to have a good prediction of that scenario. So probably we need to find some new approach to solve this kind of question, or even give a very fair approximation beyond. Finally, all the interaction happens in a relatively static interaction. But sometimes, even though we consider temporal networks, the transition of networks is independent of the interaction outcome. But I think a more interesting case is evolution happens in a dynamic environment. In this case, like the game can be like varying with the interaction outcome in the previous time step, and also the population can vary as outcome. Sure. So we have a unified framework to solve this question. I think will be very interesting. Yeah, that's the whole thing I want to show.
Okay, thank you, Andrew. And do we have some questions from the audience?
No, go ahead.
Yes.
I had a question concerning these temporal networks that are growing.
Yeah.
Could you come back to under which rules they're constructed and when do you stop the construction?
So this paper is trying to compare the result under static networks and this like temporal networks. So the final state is determined like because we need to compare with the static networks. So the final state is determined, and the rule is for the initial one is somehow determined, but the rule can be changed. So the main result for this paper is like we find out what kind of growth rules can help to increase the fixation probability of population. So the rule is the thing what we want to discover. But the initial and the final state is determined. Thank you.
No, I have one question about this model. As I mentioned, actually, when there's no mutation, either you predict or will be C or B. I just want to confirm what actually how I understood. So whether it's going to B or C very much depends on the initial distribution. That's correct.
Yeah, when there is no mutation.
That's right. There's no.
Yes. And we often consider when there is only one mutant in the population as the initialization. This is because in evolutionary biology, we actually have an assumption of low mutation. And when there's low mutation, the population will, there will be two time scales. In the top time scales, the population will rapidly evolve to this homogeneous state. But since you have a very low mutation, you have a very low probability that there is a new mutant appears in the population. That's why we usually consider this one mutant.
And then the follow-up question: can you manipulate this network topology to get what you want?
So I think that's a very interesting question, but you definitely have you could derive the result for the fixation probability when the mutant is introduced at a random site or a specific site. And, I think it's more like an answer from control theory.
Yes.
So you definitely have the theory result, and you can, but like in practice, I don't know how to like. So
I wouldn't call it manipulation, call it actually intervention, right? Put it this way. Yes.
I suppose related to what Mr. Hu saying, then if you're given a network structure and you can sort of identify that this network has C or D behavior in the long term, can I say which component of this network is crucial in keeping this cooperative or this non-cooperative sort of behavior? So if I say that I want to remove an edge to induce cooperation, like reduce the density, can I say I should remove this component or that one, for instance?
Yeah, I think that's a very good question. The answer, I guess, is still not clear, but I know what kind of thing you mentioned. Is like we have a little surgery of the networks and to see if this surgery can dramatically change, for example, the critical ratio for the population. And so for this paper, they actually did some research. So if you look at this one, so this graph, they have infinite critical ratio, which means the population can never be involved in this kind of population structure because the ratio is infinite. But if you connected connected a line between these two nodes and we call it this. So for a larger one, this network we call a ceiling fan, and in this case, the critical ratio will be a finite positive one. Then this network can promote cooperation, and we call it like network synergy. But we actually don't know how to select an edge to delete or to add to like increase or decrease critical ratio. So yeah, I guess it's a case by case study. Yeah, but I think it's a very interesting question. I hope we have like future discussion on this topic. Yeah.
To the question that you just discussed. And I mean, your question is somehow related to the graph theory. And I know that in the graph theory, there are some algorithms that you can rank the degree of we say importance of each node.
Yeah.
And but that importance or degree is kind of related to the connectivity. So I mean, if you are working with the game theory on this network, I'm not sure whether that algorithm will help. There is some algorithm that you rank all the importance and the contribution of each node.
Yeah. So
yes. For example, if we see the focus on the top level of this one, clearly in the middle, the right point is the most important, I would say. So that's kind of it is case by case, definitely. Yes.
Yeah.
But I assume that if you have a specific structure of the networks, you may have some kind of more specific conclusions.
Yeah, I agree. So yeah, there is a plenty of algorithms to identify which node is the most important one. But for I guess for his case, the thing we should identify is like which edges is somehow the most important. So yeah, but this we call it centrality of the edges or those might be changes because when the updating rules will definitely affect the delivery dynamics. So I still think it's probably a case by case result. Thank you.
Okay. So regarding the time, maybe the rest question we can communicate offline.
Okay.
Let's thank you again, Dr. Anzhi, for this very retrospective and a little pedagogical kind of review for the evolutionary game. Let's thank you him again.